to share the screen as usual. Well, dear such equality participants, dear all other 7 billion of people, today we have the final shot of the lectures about time domain NMR in solid state materials. This lecture, as you know, is devoted to really interesting directions of magnetic resonances, multiple quantum NMR that can be done on a rather inexpensive time domain NMR machine. Then we go somehow via spin diffusion experiments. We'll understand how the magnetization is traveling through the sample and how to estimate linear dimensions of different domains. And then we will consider, I guess, one interesting example. And then briefly we'll discuss what you need to do if you have the time and the machine and your samples, and what you experiments you can run. So in the beginning of our lecture, in a few minutes after my introduction, you will see the experiments that Esma is going to demonstrate to all of us. Okay, let's then start with multiple quantum transitions. So I will briefly touch Hamiltonians again, not as much as yesterday, but just to fall within the topic. So we discussed that dipolar Hamiltonian. It can be expanded into additives, and these additives they contain different types of spin operators and the spatial equations. Then two of them that are called E and F, they are responsible for so-called double quantum transitions if we can consider a system of two spins. Well, we also talked about density matrix, and we noticed that there are these light blue guys who show us the double quantum relaxation. From the point of view of energy levels, if we don't have any dipolar coupling, actually we have only one type of transition which happens on the NMR resonance frequency. And nothing interesting is happening, and we see just narrow one line. But if dipolar interactions take place, then the levels of two spin system will behave really more interesting. The two mixed conditions that you see in the middle, they will somehow split, and then we will get two different frequencies that normally form the peak doublet that we already discussed yesterday. But what's more interesting then is the case when two spins come to other condition. It means they are in the terms of vectors, they flip simultaneously. This is bringing us the double energy, and this is called double quantum transition. So here you can see also another representation of all these quantum levels. So you see this E and F, they are happening between main states of the main component of the dipolar Hamiltonian. And then of course this component which is called B, the B part of the dipolar Hamiltonian will be interesting to us when we will come to spin diffusion. Okay, so this is a brief introduction. So if you have a system that contains at least two spins, you will be able to see double quantum NMR. If you have three spins, you will be able to see both double quantum and the triple quantum. Okay, let's go on. The pulse sequences. I try to be again maximally simple. You need to excite so-called double quantum transitions. You need to have to generate any multiple quantum multiple quantum transitions, you must have so-called transverse relaxation active. To make it active, the best way is to apply 90-degree pulse. You apply 90-degree pulse, and then while your magnetization in transverse plane still exists, you apply another one. And that guy is generating all possible transitions in the spin system. As I mentioned before, in two-spin system, it can be maximally transitions with the order of 2, +2 or -2. Then these guys are generated. Actually, the generation of these transitions happens not immediately. And the stronger dipolar Hamiltonian, it means the stronger dipolar coupling, it means that you are deep in crystallites, for example, then this case of generating of multiple quantum transition is faster. If your dipolar contribution is extremely low, like in liquids, you will not get considerable conversion of the single quantum to double quantum transitions from C to D. Then it means that this technique is applicable normally only to solids. Well, we generate double quantum transition, then we can vary this interval, which is called T1. We can call it evolution, and if we vary it, we can observe something like a double quantum relaxation. It's not really bringing some new information. It's not frequently used in modern time domain NMR experiments, so that's why it's normally kept quite short. Then you need to reconvert this double quantum into, as we call, longitudinal magnetization. For that reason, it is used another pair of pulses, and they are doing again the reconversion to all possible levels. But to filter out the right coherence order, you need to perform special procedure of phase cycling. Phase cycling is something that you are changing phases of your excitation pulses, and also you are changing the phase of your receiver during acquisition. So then the right transition, in our case, we need to have this delta P, it should be -2 from +2 to 0, it should be -2. We need to perform a kind of discrete Fourier transform. So this exponent, this is something that we are doing during acquisition of complex signal. We in modern NMR, all detection is happening in so-called quadrature way, where you have real and imaginary part, and it means that you are magnifying, you are multiplying your signal with the exponent with the complex frequency. And this complex frequency, in this case, will contain the additional multiplier that will correspond to the Fourier transform of the coherence order that you need to get. So after applying these phase cycling techniques, actually you will see how this phase cycling works when Esma is going to demonstrate it slightly later. We will get the filtered double quantum signal as the observable FID in the time domain. It will you will observe anyhow the single quantum transition, but this will bring the information about double quantum levels. Okay, so this is how to make it experimentally. Now we will talk about double quantum filter, and when I finish this this on next page, we will ask Esma to demonstrate it. Well, for this sequence, varying the excitation and reconversion time, you can do really interesting thing. So the shorter excitation time, as I already mentioned before, the more strong dipolar coupling will be able to reconvert at a shorter excitation time during this excitation period. When you increase this guy, then it's needed less power of dipolar interaction to generate the double quantum transition. But the next case, as I mentioned to you before, this time of excitation, we vary it, we vary this time. If it's to make the double quantum case, you need to have the transverse magnetization active. But we understand that the strongly coupled dipolar systems, like deep crystallites, they have quite short T2. And then it means that if we increase this excitation time more, so the contribution of these crystalline regions will be in the beginning, initially it will be quite high, and then it will go down with the relaxation of crystalline magnetization. It means that increasing excitation time, we are going to make a kind of scanning filter. The longer this time, the less coupled dipolar systems we observe. It means that if we use short excitation time here, we can filter out, we can look only at crystallites. If we increase this guy, then we will be able to look on to the amorphous regions, and the crystallites will be not visible. So I guess now I will show you also this picture, how we align different signals. So we can modify this double quantum filter time. This is tau excitation. The shape of the dipolar line is changing. So initially, when you apply magic sandwich echo, you will get, this is actually dry cellulose, I guess. You will have a kind of such a dotted line, no filter. So this is typical. This is classical FID, classical MSC, and then getting spectra for them. If we apply the really rigid double quantum filter, so we look only on the strongly dipolar coupled spins in rigid areas, we will get, you see, the doublet with a really deep gap between two lines. It means we are acquiring strong signals only from crystallites. And if we, for example, increase this time of double quantum filter to 30 microseconds, we will get the narrow line, which is much more narrow than the crystalline line. It means we are getting signals, we are filtering out signals only for amorphous part of cellulose. And here I can show you double quantum filtered magic sandwich checker and magic sandwich checker. So you see black line, it shows you the spectrum of a sample, and red line, this spectrum, but where you somehow edited this dipolar part, and you subtracted, let's say, you killed any water or whatever. So now to show it how it is happening live, I would ask Esma to share her screen, or first maybe share her camera.
Yes, can you see my camera right now? Yeah, this is typical thing that we made. We will put our sample. This is starch sample, corn starch, without any treatment actually. We will put our sample and we will go directly to software. And I will share my screen. Can you see it?
Yes, we do. Yes, we can.
Yeah, then we can start with just a classical MSC, classical FID measurement. I will just run the measurement firstly. We will get FID.
We need to tell to people that in this free induction decay that is recorded by Magic Sandwich Echo, you see the water contribution. You see this light line. The water contribution is long component, and you see the polymer contribution that is a solid component. So you see both signals. Let's say soft. It's not really liquid. It's soft, and it is rigid. Then, Esma, you can show the FID in X5 plot and also the spectrum.
Yes, maybe we can just make zoom first to see the yeah. We are getting some signal from solid phase, the amorphous phase, and the long component water phase, and we can obtain the normalized signal. But let's correct the phase first to get better curve, and then we can obtain the spectrum. And here we are. This is spectrum that we obtained. And this the narrower peak is coming from the long component filter, and these tiny doublets coming from probably the amorph or semi-crystalline part, and we have some other doublets in here. But if you make the double quantum measurements, it will change totally. And I will close it right now, this measurement, and I will go to double quantum filters MSE. But in that point, we need to just change the excitation time from.
So I guess initially you make you will make quite rigid filter. You put there something like 6 microseconds, I guess.
Yeah. Okay. I will start with 6. Then I will run our measurements, and we will see the change in the spectrum.
You need to mention that that it's needed to use phase cycling to get to measure the signal, the double quantum signal. So phase cycling means that we are changing phases of pulses, like we discussed before, and now you are observing in live condition how the NMR signal is changing while we are phase cycling, and what will be as the result. So after the final 4th stage, you see how the water contribution, the long component contribution, goes down, and the rigid contribution is rising. Okay, Esma, it's your turn.
Then we can see again, this is rigid part, and this is amorph part, and it's the longer part, it's getting more. Then we can go to obtain our spectrum, and we will make this long component filter to obtain a smoother curve, and we will get our graph. You can see that we don't have any longer components, and it's just plot, just a line around 0. This means that we don't have any longer components after that point. And if we obtain the spectrum, we will see good doublets. We can see the gap between the doublets, but if we change the excitation time, if we choose the longer one, we will see that this will be just going like that, maybe even more narrower. Let me make it to see the difference. Okay, I will change from the code again, and let's make it 15. You can again see the change in the signal. The solid part is going, the signal from solid part is getting high, and the longer part is getting smaller. Okay. Okay, I will go to Untitled again. Let me clear this part to see in a good way. If we get our curve, we can see that the crystalline part maybe it's smaller, and we will see in the spectrum that it will be in that way. We can see that the gap is getting smaller and it's going up, and the distance also changing. And we can maybe try the higher one, really higher one. And we also tried many combinations, and I will show them in a separate file in Origin to make it clear. So actually, Dr. GRUNIN already showed you, but it can be additional information for you.
Yes, now you are going to see really low, really slight dipolar interaction filter. So we are going to see only the amorphous part, the tail of amorphous part.
You can see the difference in here. It's really small rather than the previous ones. And I will make the same procedure. And obtain the spectra.
You can notice that the signal decays for longer time, and this is we are catching just very small tail of the FID, and then we observe signals. We get the really narrow line. Narrow line. These oscillation, of course, they can be much smaller if we apply more scans. Though you can see that we don't see any doublet, don't see any crystalline contribution. Yeah. So Esma, now you can go to your origin.
Yes, of course. And here it is, but it's kind of small. I'm not sure you are able to see it, but this is six. The excitation time is 6 in that curve and this curve. And if you make it 15, it's like that. And this is 22 and 30.
And now that's important. So we see that this is nearly on the level of noise, but you can open the orange one, the previous one.
Of course. This one.
No, this one, yeah. This one. You see, there is no doublet at all. We see only amorphous signal contribution and maybe slightly the very bounded water. So it means that we are filtering, we are scanning the sample, and we are can excite different parts of sample. And also you can show the graph that you obtained with the dipolar filter. Yeah.
Yeah.
No. I mean the dependence of the of this.
Yeah. If you just count. Sorry. Yeah. Close yours, of course.
Yeah. Changing the time of excitation, you see that you can concentrate on different value of the polar constant, and the higher value, the more crystalline part; the lower value, the more amorphous part. So this is something like this.
This one is higher crystallinity. This one is coming from the lower.
Yeah, that's already nice.
Yes. And this is what it looks like. Do you want me to make something else?
Okay, Esma, thank you a lot. I think we now are going to continue. So maybe at this point, if anyone might have questions, that's really essential part of the talk. If anyone is listening. Okay, I think everything is clear. So we have discussed the double quantum filter. Double quantum filter, how we can select the areas of sample that we excite. Now we will talk slightly. We'll touch the really interesting experiment, which is called build-up curves for double quantum. So now you have looked at how we change this excitation time, and we plotted different spectra. If we do it sequentially, if we start with really low dipolar filter value, and then we'll just increase this excitation and reconversion time, depending on the phase cycling, we can acquire two types of curves. This type of curves that normally called pure double quantum and reference, or like it's mentioned in some publication, some of multiple quantum transitions. Actually, these are transitions from odd coherence. So the text here is clear. I guess you can read it yourself. So varying this excitation time and recording the points, we can get two interesting pictures. Then we can use them to do the following interesting trick. The idea is the following. So where is the reference signal? That is the following. We divide the black curve double quantum. We divide it onto the complete relaxation. It means double quantum plus reference. And then we will come to the case where with this double quantum and reference, they finally become equal. And we are coming to the value of 0.5. So this shape, this is called double quantum build-up curve. In fact, it is the sum of many different dipolar constant contributions. So having different polar constant contributions, we summarize all that and finally come to a kind of smooth line. So this line carries information about the distribution of the polar constant, the normalized curve, like here. And it is really already used for measurement of soft elastic samples like rubbers of soft plastics. And lots of investigations were done in Italy and in Germany in different institutions about these cases. For today, you have seen the application of double quantum sequences to rigid samples. That is actually not so much spread at the moment in the world. But the idea for solid samples, we also can try to get the distribution of the polar constant. But once we have really fast decay of the magic sandwich echo, we are not strongly influenced by the inhomogeneity of the magnet, and so the distribution of the polar constant can be also derived from the shape of the solid line. So actually this simulation, together with the experimental curves for starch sample, simulation was done according to the also experimental data, but from the spectrum. We have taken the distribution function, actually the spectrum is a distribution function of different frequencies. We have taken all these guys and multiplied by squared sine. Squared sine, I can remind, it is coming when we reconvert the double quantum into the evolution. This squared sine, square sinus. After this integration, you see the red line. It looks more or less similar as the double quantum acquired for the same sample. So it means that this double quantum approach does work and does give the good information. So in case we are not able to obtain the spectral resolution, we can use double quantum to look at the distribution of the polar constant. This is important. So the really perfect professor Kai Salvachter, he is offering so-called Abraham-like function to fit these types of curves, but it really works for more for soft polymers like rubbers. What we can get from double quantum experiments? Let's try to look what we can get. So here I show two FID signals measured by magic sandwich checker for really different samples. One of the sample is amylose. Amylose, you know, it's a part of starch, and also fiber cellulose. You see that the transverse relaxation decays different, but not so much. The idea behind that, why they are not so much different, it is coming from the basic structure, because cellulose and amylose, they have the similar basic unit as a glucopyranose ring. And this ring is forming the shape of NMR spectrum. So, but if we acquire the double quantum build-up curve, we will see strong and really remarkable difference in behavior of this double quantum build-up curve, because it looks more precisely of the distribution of dipolar constant that is defined not only by the monomer unit, but also on the crystalline and amorphous structure. Of course, crystalline and amorphous structure for cellulose and starch, they are totally different. And you see there are actually two types of cellulose, microcrystalline cellulose and fiber cellulose, and they give nearly similar behavior in the double quantum build-up curve, because they have similar structure of crystalline regions. But the amylose starch, it behaves differently. So one of the application of this build-up curve is to get a more fine resolution on the structure than we can get from the MST or FID measurements. This is really a remarkable case. Another thing that can be applied is to try to clarify how the correlation function of molecular motions can look like. So this technique, I would say again, this is really well developed by Kaja Salvatore for amorphous polymers with entangled chains that can be somehow described by the Rose model of the molecular motions. So the approach is very simple. They are taking the double quantum normalized curve and then divide it onto the squared time of excitation. And then you will get something like this. Unfortunately, this approach is not really developed up to now to carry it to the rigid polymers, because the motion type, movement type of molecules is different, and we are not able to implement time temperature superposition. But nonetheless, this is in the progress, and actually investigating the correlation function of motions in crystalline and amorphous parts of sugar type materials, what is needed for such a quality. It might be a good case to investigate while we still have this project, and even longer. So this is that is what about quantum. So you have some kind of guess what is it? Is it related for? Or what is the reason? What is the idea, and so on. And now let's come to the final theoretical and somehow practical part of our lectures. It is transfer of magnetic polarization inside the sample. That is happening due to the effect of spin diffusion. As we talked already, any rigid, any solid sample normally is not continuous. It has heterogeneous structure. For let's say for a general case, structure can contain crystal part, amorphous part, and something in between that we call interface. What is interesting that relaxation of all these guys, NMR relaxation is different. And we can use this difference in relaxations to try to carry the magnetization between the domains, between, for example, amorphous and crystalline domain, or between interface and amorphous domain, or whatever. Carrying the magnetization, the transfer of magnetization normally takes time, and this time can be somehow referred to the dimensions of structural domain sizes. Well, there are actually two ways how to generate this transfer of magnetic polarization. First, and the most simple way is to use so-called Goldman-Shannon approach. The idea is following. We apply quite simple pulse sequence, and we generate the magnetization only in soft part of the sample. and in rigid part of the sample, magnetization is 0. For example, if you apply one pulse, 190 pulse, all parts of sample will be magnetized. But if you apply 2 more pulses, you can do the following. You can make this magnetization in rigid sample becoming much less. In such a case, this is Goldman-Shan experiment, the magnetization will flow due to spin diffusion from soft parts to rigid parts, from amorphous to crystalline, from adsorbed water to porous structure, or whatever. So the basic physics behind that is the B part of the polar Hamiltonian. B part of the dipolar Hamiltonian is responsible for so-called flip-flop mechanism of dipolar interaction. So the magnetization is traveling through the sample, but it is the diffusion, but it is diffusion of magnetization. It doesn't carry any energy or any material. It means this is not material diffusion. And once it does not change the geometry, the spatial distribution of anything inside the sample, this diffusion does not change the entropy of sample. It means it can be even reversed. Really interesting case, but it is more interesting, I guess, for theoretical physicists than for practical food scientists. Anyway, so the diffusion coefficient depends on the Hamiltonian, and Hamiltonian depends on the structure of a sample. It means you can measure FID, you can measure solid echo, you can measure second moment and get the diffusion coefficient for amorphous part, for interface part, or the crystalline part. Then knowing the diffusion coefficient, then you can implement so-called initial rate approximation. The idea is the following. You are changing the diffusion time, and the longer diffusion time, the more far magnetization is traveling within a sample. And in the coordinates, like the linear amplitude of the transferred magnetization versus the square root of the diffusion time, you get some areas of these curves linear. So when we take this initial part of the curve and make the linear approximation, initial rate approximation, we can come to the values of so-called t square root of the time. This value is square root of the time is proportional to the distance that the magnetization is traveling through. It means it is proportional to the dimension of the corresponding domain, which is used, which is focused by the parameters of pulse sequence of Goldman-Shan or whatever. So you can transfer polarization from soft to rigid, like Goldman-Shan sequence, or you can do it from rigid to soft using the hard double quantum filter. You already know what is double quantum filter. We just saw it not long ago. With double quantum filter, as you remember, we can, for example, make the magnetized only the rigid part of sample. So then we can do the following things. We magnetize here, here it is nothing, and the magnetization transferring in this direction. So, but every time you, of course, need to get some guesses, some preliminary understanding what should be the structure in general to understand from where and to where this magnetization is flowing. Then once you define that, it is just the matter to get this square root of the time and get the distance and get the dimension of the domain. And you see here, you can use the spin diffusion coefficient that can be measured from different type of NMR experiment, like magic sandwich. So for more complex systems where there are different, so for example, this magnetization traveling from rigid to soft through rigid and through interface layer, you can involve different phases with different diffusion coefficients, spin diffusion coefficients, and then you can, for example, get the thickness of the interface domain. Well, so I think this is something that we discussed. In the Goldman-Shan experiment, I'm coming again to something that I was talking about. The we discussed yesterday spin lattice relaxation, like there is the internal part of a crystal and the outer part of a crystal, which we call amorphous for, let's say, polysaccharides. And we can make magnetized only the amorphous part, the Goldman chain sequence you see. We generate one pulse, then we may apply pulse in opposite direction when the signal from crystalline is dead, but from amorphous is still alive. And then we vary the time of spin diffusion and we acquire such graphs, so we can try to estimate this square root of the time and then come to some dimensions. For example, in this experiment, we have measured the thickness of water layer on the cellulose fibers when the samples were had different humidity. So here I would also make a kind of discussion about how to select the right excitation times for Goldman chain sequence. So, for example, if you want to excite only amorphous domain by Goldman chain, want to excite crystalline domain, you first acquire MSE, then deconvolute it into amorphous Gaussian signal and the crystalline, that is oscillating signal. That is great that oscillation has the point where it's crossing the zero line. It means here this time, for example, the magnetization in crystalline region is 0, so we can apply the second pulse exactly at the time when crystalline does not have any magnetization, and then after the second pulse we will have magnetization only in amorphous region. Then we can see how it is being transferred from amorphous to crystalline, or even to adsorb water. And based on this estimation, we are considering the LM. So we measure magic sandwich checker to estimate to get to know the ratio between, let's say, amorphous liquid and crystalline part, and also to get idea about the diffusion coefficient. So diffusion coefficient, we calculate the second moment from the line, and we calculate the effective diffusion coefficient. Then this graph shows you how the crystallinity and amorphicity depends on the humidity of cellulose fibers. Then you can do this Goldman chain in different directions, as we discussed before. We can carry it from water to amorphous, or from amorphous to crystalline regions. Here we try to, for example, at this place we try to estimate the thickness of amorphous layer. Let me show you. Of amorphous layer, there is red here. Maybe actually even thickness of amorphous layer towards the center of the crystal, and it was estimated with the Goldman chain selected with the selection that is shown at this picture, and real physical microfiber of cellulose was measured. So the pore depth was measured with the Goldman chain sequence, and you see how interesting it is. With the water content, the pore becomes deeper and deeper. Okay, I think this picture is showing you how this can be estimated, how the model looks like at the different stages of humidifying. You see how the structure of the fiber is changing. So at low water content, we have only just surface water, and higher water activity, it is penetrating into pore and make it deeper. And then at even higher water content, the pore becomes deeper, and this depth we are measuring with Goldman chain. That was just a simple real example how to implement one of the things to one of the described techniques to real samples. Well, Now I would like to just come to the very end and slightly summarize what we were talking about these 3 days. If you have some samples, we will talk only about actually the condensed sample that are solid, that are not liquid. In such a case, samples can be semi-crystalline, they can be either amorphous, they can be soft, or can be rigid. And all that can be somehow systematized to be studied by the time domain NMR. So this table is of course made for beginners, but I guess it should be somehow informative. So first, when you have any sample that you want to investigate, you need to look at the FID signal. What you can see, if you if in FID signal you see the fast relaxing component, even a few percent of the total amplitude, the fast relaxing component, we mean for rigid samples at room temperature, it is not longer than 60 microseconds. Then if such a component exists, then you have something rigid and you can implement many different pulse techniques. In case this component does not exist, you are dealing with something soft. Of course, not liquid because you didn't take the liquid sample. For the, let's first consider the simplest part. If you are dealing with a soft sample that don't have any rigid parts inside, you can measure T1, but T1 will not be really informative in this case. The more optimal sequence is to use CPMG or HANA echo decay to investigate the transverse relaxation. In such a case, you can look and probably detect 1 or 2 or maybe 3 components in the T2 decay. And of course, now you know that the amplitude of each component is proportional to its contribution to the structure, and the relaxation time is actually proportional to mobility. The longer relaxation time, the better mobility. So for soft samples, HANA echo decay or CPMG, it's actually the best things to do any kind of investigation. Actually, double multiple quantum experiments also are possible, but actually they are really described in the publication of some really nice. So I don't want to put a lot of attention to this. But if your sample has something rigid, then you can try to apply whatever you will study during these 3 lectures. For example, first you need to do. You need to measure, to look at the T1. You need to make the T1 experiment and see how the magnetization is coming to equilibrium, and try to monitor the T1 curve for rigid part and for soft part. Maybe, possibly, they will have different T1 values. Then it is really interesting and useful information. Then you can think about how they are close to each other, how they interact to each other, and so on. As you remember from our yesterday lecture, T1 is growing with the growth of crystal size. If crystal dimensions are big, then you normally have higher crystallinity in the most of cases. So something like crystallinity, amorphicity, and crystalline dimensions, what you can gain from the T1 measurement. And of course, T1 is needed to measure all other experiments, because you know, so the relaxation delay between when you're scanning the measurement, it should be at least bigger than 5 values of T1. So that's first measure FID, then measure T1, and then you can go following directions. You can measure magic sandwich echo, solid echo, more precisely with more accurate scanning, and then get what we discussed. You can get crystallinity, amorphicity. You can get different phase ratio, like something movable that can be water, oil, or maybe soft or solid fat or whatever. So this is about the content. MSE can give you information about the content of different phases of the sample. Then what else you can do? If you have the long component, if you have rigid part and also you have the long component, then you can implement also the CPMG experiment with quite a short echo time, quite short time between 180 pulses. And then you immediately get information about mobility, about dynamics of the long component. For example, we do lots of measurements in cellulose type samples, and there is always water in cellulose samples unless you dry them. And this water is interestingly showing up at least 3 components in the CPMG experiment. So we can distinguish water from micropores, water from mesopores, and water in big pores. Of course, contribution of all these waters into the whole humidity, and also the difference in dynamics, different in mobility. So this you can do in case you have long component. For example, starch, for example, hard candies, soft candies, most of them, I guess, they have a kind of long component. Then, of course, it is very much interesting to measure any dimensions. For these reasons, you can use speed diffusion experiments that can be based on Goldman-Shan sequence and can be also based on the double quantum excitation, double quantum filter. So you measure spin diffusion and you obtain but it's very important to construct the experiment in a very correct way, and you obtain the idea about linear dimensions of your crystallets, for example, or your interface layers. Then, if you already read books more, you can do double quantum, multiple quantum, look at the shapes, and maybe do some interesting fundamental ideas about the correlation function of molecular motions, or about the structure of crystals, or whatever. So this is, I think, most of the ideas are summarized in this slide. Then, but this is only the beginning. This is all done at a fixed temperature. But you know, the time domain NMR, says all NMR, depends on the signal, on the mobility of nuclei or molecules within. And this mobility, of course, can be modulated mediated by the temperature. So, classical thing, you vary temperature depending on the sample. You change the temperature, you see the dynamic is changing, and then at each temperature step, you can measure all these guys, and then you get lots of information, lots of arrays of information, and of course you can implement the knowledge of physics, or you can just use what is modern now, the data science, to find the correlations by the helps of robots. So I guess this is all what I wanted to tell within 3 lectures. Well, thank you very much.
Thank you, Dr. GRUNIN. So very nice, and I think it will be really a good material for us time to time to visit and check while doing the experiments.
Yes, you know, I was trying to, once we have many people in consortium who never saw time domain NMR, I tried not to focus on the performance of definite relaxate software because they don't know what it is at all. I tried to make the idea about all that. Then I guess while using our secondies, we can think about something that can tell, like ESMA today showed really nice things, how to use the definite software and definite tricks to perform this and this sort of experiments on a definite instrument. Okay, so your questions, yes.
Okay, so basically I have a question for you. By the way, are there any questions from the other audience already?
I think I'm telling everything very clearly. Everybody understands.
Well, the issue is usually, you know, you try to ask some of the questions when you do the experiments yourself. And I guess probably as this was really helpful presentation, once we start and the secondies start doing the Q or spin diffusion experiments, they will visit this presentation and they may bother you through email.
Okay, I have one question.
Okay, Maria.
I would like to clarify one thing. Can we return to dipolar filtering of signals?
Double quantum filtering, right?
Yes, double quantum.
Okay, at what place?
In origin.
That Esma showed.
Yes, yes.
Okay, Esma, are you around?
Yes, I'm here. Yes. Okay.
Can you please open that origin file again? So Maria have
Alright,
questions.
so let me. Okay, they open soon.
To origin.
Yes, yes, but it's took some time.
Because you know origin takes time.
Is it still the older version of the origin?
Yes, the one that I really love, but it looks like it is stopping working on all modern Windows.
This is origin 7?
Yeah.
Yes. Okay.
Okay.
Mm-hmm.
Okay, and my question is related to the graph
This one?
SSL. Yes, this.
Yeah.
And how did you calculate the polar constant? Is it related with the second moment of filtered signals? Here.
Yeah, really good question. Esma.
Yes. We calculated it by just deciding the maximum amplitude and the half of it. Let's say we can find the maximum amplitude by looking at that value, and we find the half of it, let's say around here, and we just measure the distance between these parts, and we put in a graph that this is for 6 microseconds, and we calculated for separately for each excitation time, and we just draw the graph.
So
this is the half distance of the amplitude.
So Maria, this is the way of calculating the width of the line on the half height.
Yes, I understand.
So this is the way they calculate it. This is one of the way to get something related to the dipolar constant. You can measure second moment on or as it's normally done in theory of signals, you measure the line on a certain level, on the 0707 or on the half of width, and then you get this this parameter.
Okay.
So are you satisfied?
No. But okay, how to say, I will read in books.
Yes, this is just one of the simplest way to estimate something that is proportional to the dipolar constant. This value should be totally proportional, behave similarly. The other thing is the absolute value, whether it is 60 kilohertz or maybe this is 35 kilohertz. But the line width is a kind of second moment. Of course, if we talk about the homogeneous line somehow can be really different. Then you are absolutely right. It's needed to integrate the spectrum.
And the second question is about which dipolar constant we talk now, about static or residual?
We now talk about the everything residual. The static one can be adopted, can be acquired when you make the build-up curve, and you normalize the double quantum by the sum of the all quantum things. And the initial rate of the build-up curve will depend only on static dipolar constant. For this, we use just the double quantum filter. It means it depends on temperature.
Mm-hmm. Okay. Thank you.
Yeah, really good question. Okay.
Thank you, Dr. GRUNIN. Any other questions?
Hocam, can I ask?
Sure, Shiron.
Hi, Dr. GRUNIN.
Hi,
Can we
Shiron.
go to slide that the spin diffusion with Goldman chain and also double quantum one?
Okay. Esma, I think you need to first stop sharing. Then I will switch to my
Of course,
screen.
of course, of course. I'm sorry.
Huh? No. Okay, Shirvan, where? Please repeat again. Spin
The
diffusion.
bit, yeah, not this one. Yes, yes, this one. You know, we have yes, double quantum spin diffusion one and the Goldman chain one, and
Yeah.
these are the different directions, right?
They go in different directions. Exactly.
I got confused here. Normally in Goldman chain, we are doing we are calculating actually the transfer from long component to short component,
Exactly.
right?
Exactly.
But the double quantum one, it's going another direction because we are filtering the long component. But normally it's there. But we assume that it's not there, right?
You know, with a double quantum filter, you can do whatever. If you apply a really long time of excitation, you can even transfer magnetization from long to short. But this is not reasonable at all because you need to do many phase cycling steps and the amplitude will be low. So to make the transfer from soft to rigid, it's better to use Goldman chain.
But when we do this double quantum, normally we ignore the long
What?
component one, right?
Yeah, the long component is killed after double quantum filter.
This is what I'm confused actually. We are killing it, but normally we just don't see it, right? Normally it's
Yeah,
there.
yes.
There is a magnetization over there.
Shirvan, maybe I do understand your idea. So you did the double quantum filter. It means that you pick up the right excitation time here and here. And then in normal double quantum filter without spin diffusion, this type of Z filter time of Z filter is really short. And then you see the double quantum signal without long component. Like here, you see spin diffusion time is 50 microseconds, and you see just the doublet, no long component at all. But then if you increase this Z filter time, then the spin diffusion is going on from the rigid part, from this doublet. It is coming to the center of the spectrum, and this line is growing, growing, growing. In time domain, it means that you don't have long component, but then this long component is going up because of the magnetization is transferring from the crystal. And of course, there is a natural case when it's growing up due to spin lattice relaxation, but it should be normally much longer scales.
Okay, thank you.
So that is the reason. If you don't see a long component, that's great. That it means that we completely killed magnetization in the soft part of the sample. Okay.
Dr. GRUNIN, I have a question. So can we use this filtering for also samples like honey, which is really like viscous, but we are interested in some, let's say, crystals?
In case you have anything rigid, in case you have any, maybe 5% of rigid fast component, you can implement it, and you can kill all other signal.
Okay.
If it's really small, this short component, you won't kill it completely. You can use maybe 8 steps in phase cycling, 16 steps in phase cycling, you can kill it better, but it's possible.
And what about, like, as you know, in our lab, we have 2 of your systems. one with larger coil and the other one is
Mhm.
much more homogeneous field. Can we also apply this DQ filtering on the lower field system, which has longer RF pulse durations?
In principle, yes. I don't. The thing is that I don't remember what is the dead time. What is the pulse in the dead time?
It is around, I think, okay, I can check it, but around 20. So it depends on the dead time.
It depends, and then if that time is together with the pulse, you know, for our classic system, we have that time of from 7 to 10 microseconds, and the pulse are of around 3 microseconds. So this is something like 12
exactly.
microseconds. If 12 microseconds, this sum is 12 microseconds. In principle, you can do lots of stuff on any rigid things.
Okay.
And if you have it, I guess even 20 microseconds altogether, it's not a big problem.
Okay. Thank you.
Okay,
Any
thank
other
you.
question for Dr. GRUNIN?
Hello, I have one question.
Sure.
Dr. GRUNIN, since I'm just a beginner, it may be a silly question, but normally we compare crystalline part and amorphous part and calculate the crystallinity of the sample most of the time. When we apply this filtering, for example, we applied filtering and get amorphous part signal. How do we compare? How do we interpret this data? How do we make the comparison? What are the factors that we should be careful about? How can we make the comparison?
Yeah. So then you need to have a kind of imagination. What is the structure? So just to understand where this magnetization can flow. If you don't have any rigid component, it will not flow to the rigid component. If you have it, it will flow to rigid component. To construct experiment, you know, I didn't tell anything about the detection, because we can detect during spin diffusion experiment, we can detect, you know, short component or long component or middle component and see how it's changing the time. So our idea is to see how the magnetization is leaving some domains and how it is coming to other domains. So if you excite only amorphous parts, then magnetization will leak to crystalline part. Then is the case how in the FID, what regions to select to detect and what is to subtract from that, and how to normalize just to leave only the contribution of spin diffusion. So for these cases, I never refuse answering. So I'm always online for all reasonable questions. And I'm sorry, I still didn't reply your letter. But I guess during the weekend I will process all the questions. So in case your samples, just we try measuring first MSC, then understand what we can do, and then we generate the application for double quantum or Goldman machine or whatever filter to stimulate this diffusion.
To make comparison between two different samples, for example, we apply, we fit our data first, and then we comment on the constant of our fitting, right?
Yeah, but for different samples, we need to look at all different samples initially, just to try to develop the same settings for all samples. Then we will have the power to have the race and the right to compare them. Otherwise, it's not good. Look at all samples. Look at FIDs of all samples, of MSC of all samples. Then we discuss how we organize this transfer.
Thank you.
Okay, any other? So we are almost to the end of our time, actually. So thank you very much again, Dr. GRUNIN, for these 3 days. So they were really helpful, and I'm sure we will keep using the information you provided for many years, I assume.
For many years, yeah. I will check this PPT file, then give to you, and then you can put it somewhere.
Oh yeah, we can also share that too. That would be great.
That should be okay. I will just do some additions, and then let's do this scientifically.
Okay, sounds good. So if there are not any questions more, I will close the session.
Yeah.
And I would like to thank everybody for their participation and for the questions. And as such a quality consortium, we will keep having trainings until the end of our project. So keep following us, I would like to say. Thank you very much.
Yeah. Stay tuned. Bye.
Bye-bye.
Bye-bye.